Good morning to all. I am Umasankar, Associate Professor, EEE Department, SA Engineering College. So this is my third GATE course video lecture. The last two video lecture discuss about electrical circuit theory. So today I am going to discuss about speed control of DC machine of electrical machines. So this is the syllabus for electrical machines. So I am explaining about speed control of DC motor. Why speed control of DC machine is necessary? So we know very well we need precise in application, energy efficiency, enhanced performance and extend motor life. So this is very important in the application of DC motor. For example, this is a rolling mill. So in rolling mill we are using a DC series motor. In olden days they are using DC series motor, right? So this is used for cutting the steel or manufacturing the bar, steel bar, then creating a rod. For that different speeds are required. So precise controls are important. Similarly, in elevators also we are using a DC shunt motor or DC compound motor, right? So here also we are immediately stop or start. For that different speeds are required. So precise controls are required. Similarly, in the textile industry also using DC shunt motor because it requires a stable operation. Okay, so DC shunt motor given a constant speed. Okay, so that we are using a DC shunt motor. So it requires, right, precise control of speed. And one more thing, you know very well in the car manufacturing industry, right, we are using a conveyor belt as well as robotic arms. So the conveyor belt stop in the particular position. For example, if you want to assemble any car top portion or steering, that section, if you want to move the conveyor belt, that particular locations are stopped using the precise control, right? Similarly, the robotic arms also pick the material and assembly the car. That also we need speed control. That's nothing but precise control. And energy efficiency. So suppose if you are not using the speed control method, the motor continuously run with full speed, that will damage, right, inner parts of the motor, and also overheating will be produced. That heat energy damage the insulation part of the winding. Okay, so that we are using a proper speed control for the proper application, the efficiency of the motor will be improved, right? And also we are getting a performance also enhanced and avoid the wear and tear also. So that's what that speed control is important. So first discuss about speed control of DC shunt motor. In speed control of DC shunt motor, two methods are available. One is armature control method, the another one is flux control method. In armature control method, again two methods are available. One is armature voltage control method. This is otherwise called as Ward-Leonard control method, right? So this is Ward-Leonard control method. Okay, the next one is armature resistance control method. Clear? And another one is flux control method. Now I will explain one by one. Okay. So this is the first one, Ward-Leonard control method. In what you not control method, we are using motor generator set. Okay, that is control the speed of the M1 motor. So this is the M1 motor required to adjust the speed. Okay, so this is nothing but main machine, that is motor generator set. Using the motor generator set, we are varying the supply voltage to the M1 motor. So this is M1 motor, this is M2 generator set. Okay, so here the generator voltage is varied by using the field regulator. By adjusting the field regulator, it produces different voltages. That voltage supplied to the armature of the M1 motor. So we have to control or adjust the speed of the M1 motor. Okay, so in this case, the field winding of the M1 motor is connected to the fixed excitation voltage. That means the field winding is connected to the fixed voltage. Okay, we can vary only the armature voltage. So the armature voltage of M1 motor is controlled by M2 generator set. Okay, so this is called as armature voltage control method. So we know very well EB equal to V minus IA RA. Okay, so if you are changing the supply voltage value, okay, the EB value is also vary. For example, the IARA drop we can consider 10 volt. Clear? So initially we can supply 220 volt. Supply voltage is 220, IARA drop is 10, so the EB value is 210 volt. Clear? So this is the EB value. Now I am adjusting the field regulator of the generator, then supply voltage is 200 for the M1 motor. Okay, now supply 200 volt to the M1 motor. Now what is the value of EB? Definitely the EB value is 200 minus 10. Now the EB value is 190 volt. Now the EB value is 190. So initially the supply voltage is 220. The IARA drop is fixed, that is 10 volt. The EB value is 210. Okay. If you are changing the voltage supplied to the M1 motor using the motor generator set, now fix the supply voltage is 200. Now the EB value is 190 volt. Clear? So what is the speed now? We know the relation between speed and back EMF, right? So this is the relation between speed and back EMF. So N proportional to EB divided by 5. Clear? So speed is directly proportional to the back EMF. So initially the back EMF value is EB1 is 210 volt. Okay, so the speed is also proportionately the speed is available. When the EB2 is 190, volt. So initially the EB value is 210, right? Now the EB value is decreased to 190. So the speed is also decreasing. speed is also decreasing. So this is armature voltage control method. Clear? So we can vary the voltage of the M1 motor using motor generator set. Okay? So in the same Watt-Leonard control method, we can achieve flux control method also. But anyway, we will discuss separately flux control method, right? So next, so now you know very well armature voltage control method. In armature voltage control method, using the Watt-Leonard setup, I explained, right? I think you know understand the concept. When the EB value is decreased, the speed is also decreased. When the EB value is increased, the speed is also increased, because the speed and back EMF directly proportional. Clear? Next, armature resistance control method. Clear? In armature resistance control method, in armature resistance control method, the external resistance connected in series with the armature. Clear? So in this connection, this is line current, okay, this is ISH, okay, this is IA. So now this is the external resistance. So external resistance connected in series with the armature. Okay, so that's what it is called as armature resistance control method. Clear? So here also the EB value will be varied. So I can explain with a small example. So I can consider, so EB equal to, okay, V minus IA of RA plus R external. Okay, why? Because the external resistance added in series with the armature resistance, in series with the armature resistance. So we can assume the RA value is 1 ohm, okay, R external is 9 ohm, okay, voltage is 220, voltage is 220. Clear? Now calculate the EB value and assume the IA current is 10 ampere. IA current is 10 ampere. Voltage is 220. So 220 minus IA is 10 into 1 plus 9. Okay. Now the value is 220 minus 100. Clear? So the EB value is reduced to 120 volt. Okay. Now we know the relation between speed and back EMF. Both are directly proportional. Clear? So we can assume without external resistance, right, the EB value is V minus IARA, right? V minus IARA. Without external resistance, EB value is V minus IARA. So 220 minus 10 into 1. Clear? So the value is 210 volt. So we can assume for 210 volt the speed is 1480 RPM. So we can assume, okay. For understanding the concept, we are assuming the speed is 1480 RPM for 210 volt. Now, if you are adding the external resistance in series with the armature, what happened? The EB value is drastically decreased, that is 110 volt, right? So what happened? Definitely the speed is decreased. Why? Because we know very well N is directly proportional to the EB. Okay. When the EB value is decreased, the speed also decrease. So initially the EB is 210, so the speed is 1480 RPM. Now the speed is drastically decreased, that is 120 volt, right? 120 volt. Speed is 120 volt. So we can assume the flux is also constant. Now what is the speed? Okay, for N2 by N1 equal to EB2 divided by EB1 into phi1 divided by phi2. How you are getting this equation? So this is the common equation, N proportional to EB by phi, right? So first we are assuming, so N1 proportional to EB1 divided by phi1. Okay. Similarly, N2 equal to N2 proportional EB2 divided by phi2. Clear? Now we need what is the new speed, right? That is N2 speed, because we are assumed N1 is 1480 RPM. Clear? So using this relation, the final formula is N2 by N1 equal to EB2 divided by EB1 into phi1 divided by phi2. So in both the case we are assuming the voltage is almost constant. So what happened? The speed is drastically decreased, right? Why? Because we are assuming this ratio is really, because for explanation only I am giving this example. So initially for 210 volt we are assuming the speed is 1480 RPM, right? Now if you are adding the external resistance, the EB value is drastically decreased, that is 120 volt. Clear? Then what happened? The new speed? The new speed value is drastically decreased. Using this formula we can calculate. In the later we can solve one problem. Then only you can clearly understand the concept. So using this relation we can calculate the new speed. So now what is meant by armature resistance control method? Okay, in armature resistance control method, if you are adding the external resistance in series with the armature, that will affect the back EMF. That will affect the back EMF. Why? Because the external resistance is variable one, right? Keep on increasing the external resistance, the EB values keep on decreasing. So when the EB values keep on decreasing, the speed is also decreasing, because both are directly proportional. Okay, right. The next one is flux control method. Okay, in flux control method, adding the external resistance in series with the field winding. In series with the field winding. So what is the difference between armature resistance control and flux control method? Control in the sense adding the resistance, right? The resistance only creating the control. Clear? Either it control current through the armature or otherwise it control current through the field winding. So what is the difference? In armature resistance control method, it control the external resistance control the current through the armature so that it will affect the back EMF value EB. Clear? So back EMF and speed directly proportional. So speed is also decreasing. Okay. But in flux control method, the external resistance connected in series with the field winding. Okay. So here it control the current through the field coil. Clear? And DC shunt motor, the ISH is nothing but V divided by RSH. Clear? So the RSH value initially without external resistance, the RSH value is fixed one. Now I am adding the external resistance in series with the field winding, right? So that the ISH is nothing but V divided by RSH plus R external. Clear? Now you know the difference, right? So without external resistance, ISH is nothing but V divided by RSH, right? Okay. Here the supply voltage is constant. The RSH value is also fixed. Then it produces fixed flux. Okay, fixed value of flux. Okay, because so it will be vary up to 0 to ISH value, right? So up to this value, so this is nothing but fixed one. So supply voltage is fixed, RSH value is fixed, so ISH is also fixed. The shunt field current is responsible for producing the flux. So flux is directly proportional to the ISH. Clear? So without external resistance, the numerator and denominator both are fixed, so that the ISH value is also fixed. The ISH is responsible for producing the flux. The flux also constant. That's what we can say that DC shunt motor is constant flux motor. Okay. Now you know the relation, right? So N proportional to EB divided by phi. So here the flux is inversely proportional to the speed. Okay. So now if you are adding the external resistance in series with the field winding, the ISH value is decrease. The ISH value is decrease. So ISH value is decrease means flux also decrease. When the flux decrease, the speed is increase. Clear? So flux control method is called as above rated speed. It provides above rated speed. Clear? The armature resistance control method provide below rated speed. Clear? So armature resistance control method provide below rated speed, flux control method provide above rated speed. Clear? I think you know the difference between armature voltage control method, armature resistance control method and flux control method. Clear? Next, we can solve one problem. The first one, this is the previous gate question paper. I pick one problem that is. Now discuss about this problem. Okay, here a 280 volt separately excited DC motor with armature resistance of 1 ohm and constant field excitation drives a load. The load torque is proportional to the speed. The motor draws a current of 30 ampere when running at a speed of 1000 rpm. Neglect frictional losses in the motor. The speed in rpm at which the motor will run if an additional resistance of value 10 ohm is connected in series with the armature is. What is the value? Right. So here the external resistance 10 ohm is added in series with the armature. So this is nothing but armature resistance control method, right? So this is armature resistance control method. Clear? If you are adding the external resistance, that will affect current through the armature. Clear? Without external resistance, the current through the armature is 30 ampere. Clear? So IA1 is 30 ampere. Clear? So for that the speed is 1000 rpm. Clear? Supply voltage is 280 volt. Okay, so here the mention constant field excitation. That means the phi 1 equal to phi 2. Phi 1 equal to phi 2. And the load torque is proportional to the speed. The load torque is proportional to the speed. So T directly proportional to the speed. This is given. Clear? Okay. We will check which one is the suitable answer. They mention A is 420 rpm, B is 280 rpm, C is 483 rpm and D is 200 rpm. Now solve and check which one is correct answer. Okay. So first write the given data. Supply voltage V is 280. Armature resistance RA is 1 ohm. Okay. And IA they given 30 ampere. Clear? Next, external resistance, that is 10 ohm. Speed, initial speed N1 is 1000 rpm. 1000 rpm. So to find what will be the new speed? So that is, we can assume it's nothing but N2 after adding external resistance 10 ohm resistor. So in DC shunt motor, the back EMF EB equal to V minus IA RA. Clear? Now you can calculate without external resistance what will be the back EMF. Clear? So without external resistance. Without external resistance, what will be the back EMF? So EB1 equal to 280 minus 30 into 1 ampere. Clear? So 280 minus 30, so this is 250 volt EB1. Clear? So for that, the N1 value is, they given 1000 RPM. So this is a given value. So this is the given data. The supply voltage is 280 volt. Armature resistance is 1 ohm. Then the IA1 value is 30 ampere. External resistance is 10 ohm. And speed, initial speed without external resistance, speed is 1000 RPM, right? After adding the external resistance, what will be the speed? Okay. And one more point, they given phi1 equal to phi2. Okay. Then torque is directly proportional to the speed. Clear? So without external resistance, clear? Without external resistance, find EB1. So EB1 equal to V minus IA1 into RA. So EB1 equal to 280 minus 30 into 1. So EB1 is 250 volt. And this is the given data. N1 is 1000 RPM. Okay. Next, they given the relation T proportional to N. Clear? And we know very well T proportional to, this is nothing but given. Okay, this is nothing but given in the problem. But we know very well T proportional to 5 into IA. This is the torque derivation. Based on the torque derivation, we know the relation torque is directly proportional to the flux into armature current. Clear? So in this problem, the flux is nothing but constant. The flux is nothing but constant. The flux is flux phi1 and phi2. That is nothing but constant field excitation, right? Constant field excitation. So that the flux is constant, right? So T proportional to IA. T proportional to IA. Clear? Now, without external resistance, T1 is proportional to IA1. Without external resistance, T1 is directly proportional to IA1. Similarly, with external resistance, T2 proportional to IA2. Clear? If you are adding the external resistance, that will affect the current through the armature, right? So that T2 is directly proportional to IA2. Here the T1 is directly proportional to IA1. And the problem they mentioned, the torque is directly proportional to the speed. So here T1 divided by T2 equal to, okay, IA1 divided by IA2. Okay, this is based on the theory. We know very well because as per the torque derivation, the torque is directly proportional to the flux and armature current. In this problem, they mention clearly constant field excitation. So torque is directly proportional to the current. So two type of armature current is possible. One is without external resistance IA1, with external resistance IA2. But anyway, the torque is directly proportional to IA. T1 is directly proportional to IA1. T2 is directly proportional to IA2. For that, we know the relation T1 divided by T2 is nothing but IA1 divided by IA2. Similarly, as per the problem statement, T1 proportional to N1, because if you are adding the external resistance, the speed is also change, right? So T2 directly proportional to N2. Okay, so we can consider this is equation number 1. Okay, here as per this, T1 divided by T2 equal to N1 divided by N2. This is equation number 2. Now compare 1 and 2. Compare equation 1 and 2. We get the relation IA1 divided by IA2 equal to N1 divided by N2. Clear? So here the IA1 value is 30 ampere, N1 is 1000 RPM, but we need IA2 current because IA2 is unknown. Similarly, speed N2 is also unknown. Okay. Now we finished, right? EB1 is 250 volt. Clear? IA1 30 ampere. N1 is 1000 RPM. Okay, and we know the relation IA1 divided by IA2 equal to N1 divided by N2. Now find what is IA2. So IA2 equal to, okay, IA1 into N2 divided by N1. So just cross multiply. So IA1 into N2 divided by N1, that is equal to IA2. So now IA1 is 30 divided by 1000 into N2, that is IA2. So here this is 0.03 N2, that is equal to IA2. Clear? Okay, next, now find what is EB2. So adding the external resistance, right? Adding the external resistance, EB2 equal to P minus IA2 RA plus R external. Clear? So EB2 equal to 280 minus, what is IA2? IA2 is 0.03 N2 into RA is 1 plus R external is 10. Okay, R external is 10 ohm. Okay, IA2 is 0.03 N2. Clear? Now we know the relation N proportional to EB divided by phi. Clear? So N1 proportional to EB1 divided by phi 1, and N2 proportional to EB2 divided by phi 2. Clear? Now consider this is third, this is fourth, and equation 4 divided by 3. Equation 4 divided by equation 3. Now we get the relation N2 by N1 equal to EB2 divided by EB1 into phi 1 divided by phi 2. Clear? Now N1 is 1000 RPM, EB1 250 volt. Clear? Next RA is 1 ohm. Okay, IA2 equal to 0.03 N2. Okay. Now substitute this value in this equation N2 by N1 equal to EB2 EB1 into phi 1 divided by phi 2. So as per the problem statement, phi 1 equal to phi 2. As per the problem statement, phi 1 equal to phi 2 because constant field excitation. So the formula is changed to only N2 by N1 equal to EB2 divided by EB1. Clear? So EB2 equal to 280 minus 0.03 N2 into 1 plus 10, right? So that is 280 minus 0.03 N2 into 11. Clear? Now find what is 11 into 0.03, 0.33. So 280 minus 0.33 N2. This is EB2. Okay. So substitute in this relation EB2 divided by EB1. Clear? So N2 divided by 1000 equal to 280 minus 0.33 N2 divided by EB1 is 250. EB1 is 250 volt. This is we already calculated, right? Now what is N2 into 250 divided by 1000 equal to 280 minus 0.33 N2. Clear? So this is 0.25. So N2 into 0.25, that is equal to 280 minus 0.33 N2. Okay. Now, this is 0.25 N2. 0.25 N2. So now shift the 0.33 N2 in the left hand side. Okay, plus 0.33 N2, that is equal to 280 plus 0.33. So this is 0.58 N2 equal to 280. So N2 equal to 280 divided by 0.58. Yes. Now this is the value 482.7586. So after the decimal point is more than 5. So N2 is 483 RPM. Clear? Now you clearly understand the problem represent armature resistance control method. Without external resistance, the speed is 1000 RPM, right? They're given. Without external resistance, the speed is n equal to 1000 RPM. After adding the external resistance, the speed is drastically reduced to 483 RPM. Now we got the result, right? N2, new speed is 483 RPM. After adding the external resistance, the speed is drastically decreased, right? Now check the answer. Okay, the option is A is 420 RPM, B is 280 RPM, C is 483 RPM, D is 200 RPM. So option C is the correct answer. So 483 RPM. Thank you. We'll discuss the next session, the second problem. Thank you.